I am elated to introduce Jun to you. His work, particularly on the bone-inspired infill optimization, has had lots of fun activities going on both in academia and industry, and I think Jun is quite chuffed about this, and very rightly he should be. And more importantly, on a personal note, Jun loves playing badminton. With that, Jun, over to you. Love to hear from you what you have for space-time optimization today.
Thank you for a very kind introduction, Ajit. It's a great pleasure to be here. Thanks for having me. So let me share my screen. Okay. Can you see my screen?
Yep, nice one.
Perfect. So hello, everyone. Welcome to my presentation. As introduced, my name is Jun. I'm an assistant professor at the Delft University of Technology. My research has been focusing on topology optimization and design for additive manufacturing. In the past few years, I have mainly working on multi-scale topology optimization to design hierarchical structures or to design lattice structures. And we have recently published a review article on this topic. Today, I want to talk to you about an exciting new research direction we started to explore recently, which we call space-time topology optimization. So here, space refers to design of structural layout as in standard topology optimization. The innovative part is we bring in the time dimension. The time dimension encodes the fabrication sequence or the process order according to which a structure is fabricated piece by piece, layer by layer. The exact meaning of this time dimension will become clear later in my presentation. So in space-time topology optimization, we want to design a structure and at the same time plan the fabrication procedure to realize the structure. And this will maximize the performance of structures produced by additive manufacturing. The concept of space-time topology optimization is relevant for additive manufacturing in general, but I'm going to explain the concept using robot-assisted manufacturing. So let's have a look at this futuristic scenario where a bridge is constructed by autonomous robots that move along this bridge. So here clearly we have two tasks: to design a structure and to plan the procedure to realize this structure. And typically these two tasks are performed consecutively. And when we design structures, we are primarily concerned with the mechanical load for the entire structure, for the entire mechanical component, the traffic load for the bridge, for instance. However, if we look into manufacturing process, in this case, using wire and arc additive manufacturing, using robotic platforms, this manufacturing process introduces process-dependent mechanical and thermomechanical loads. And these mechanical loads are critical. If they are not considered in the design or not in the process planning, they may result in catastrophic failure during or after construction. And these mechanical loads also result in very large distortion during construction or when a bridge has been constructed. Furthermore, additive manufacturing process in metal additive manufacturing, because of the phase transition, because of the high temperature gradient and the thermal history, they all influence the development of microstructures and residual stresses. This essentially means the material properties of fabricated structures will be different from what has been assumed when we design the structures. So the point I want to make here, which previous speakers have also touched upon, is the performance of additively produced products depends not only on the structural layout, but also on the fabrication sequence and the local process conditions. The local process conditions such as laser power, travel speed, and these have been discussed in previous talks. And here I'm mainly interested in structural layout and fabrication sequence. Talking about structural layout, it has been very well recognized in the community to design using topology optimization. So I just want to briefly show this animation, just to, if you are unfamiliar with it. So in topology optimization, the structure is discretized into elements, and each element will be able to have material with no material, and the topology optimization essentially transfers structure design into a material distribution problem. So to the end, topology optimization is able to find very optimized structure for the intended load case. In this case, a load is applied on the right-hand side. So this is very well recognized in the community, exploring the flexibility of additive manufacturing. What has been less researched or less recognized is the importance of fabrication sequence and how the process order may change the material properties. The machines are numerically controlled. They have great flexibility, especially with the emergence of robot additive manufacturing. They have more degrees freedom, 5 or 6 degrees freedom. They can translate and rotate the model or the nozzle, so they can allow to accumulate material along curved layers. So let me show you this video. So here in this platform with a robotic arm, it rotates and translates. Here, the purpose is to reduce support structures. But in metal additive manufacturing, we can make use of this added degrees freedom to control the mechanical properties of the materials. A question here is, how can we encode the fabrication sequence so allow us to have a systematic way to find the optimal fabrication sequence? And this is the motivation of our work space-time topology optimization. And this is a central slide illustrating the idea. So we have two design fields. The first one is a density field as in standard topology optimization. So here, this rectangular domain is the design space. The density field is a binary field. It's either 0 or 1, meaning when a structure is completed, this will be the structure and this part will be left empty. The innovative part here is we introduce a time field to encode the fabrication sequence. The time field is normalized to be between 0 and 1. 0 essentially means it is the build plate. It will be produced at the very beginning. And 1 means it will be produced at the very end. The time field is a continuous one, so it has a continuous distribution from 0 to 1. If we have this scalar field, we compute isolines like 0.2, 0.4, and 0.6. And these isolines can be interpreted as 2 paths to realize this layer. And from the density field and time field, we can compute intermediate structures during construction. For instance, here I showed 2 slides during showing 2 from a sequence of intermediate structures. So here, 0.2 means 20% of the structure has been produced. On the right side, 0.4, that 40% of the structure has been constructed. So this is how intermediate structures are derived from the density field and from the time field. So with this encoding, we embedded into an optimization workflow. So we have 2 sets of design variables, a density field, a time field. From this, we can compute a series of intermediate structures. In our implementation, the number of intermediate structures is prescribed, like 10 layers or 100 layers. From this, once we get intermediate structures, we do functional analysis. Important here is we analyze not only the final structure, the complete structure, but also all the intermediate structures during the construction. So this means very intensive computation to analyze all the properties during the continuous fabrication process. And from the simulation, we extract information of important information to minimize or to maximize, for instance, to minimize distortion, to minimize residual stress. Of course, we also have constraints. And this objective function depends on the density field and time field. It is also related to all the intermediate structures. And by using gradient-based numerical optimization, we update the density field and the time field. So this is an iterative process. In each iteration, we would simulate a series of geometries for the entire fabrication process. I'm not going to explain the details, but I will already jump to some of the interesting results I want to share with you. The first one is similar to the bridge scenario I showed at the very beginning. So here we have a design space, a rectangular design space. The left side is fixed. A structure will be found in between, and this structure is supposed to support a load applied on the bottom right side. We assume this structure will be produced by a moving robotic platform. The robot will move from P0, P1 until P7, and at each point, the robot has a given amount of material to deposit. So the objective function consists of two parts. The first part is the compliance of the entire structure, the compliance of the structure after it has been fully constructed. And the second objective, the second term is the compliance of intermediate structures, because for the intermediate structures, they are subject to the gravity of this robotic platform. So we also want to minimize the distortion of the structure when a robot is moving on top of it. And here we assume the load of this robotic platform is constant. So this is the objective function, and let's have a look at some interesting results. So here, the robot is moving on the top. To the end, you see a structure, the cantilever beam, similar to what, to some extent, similar to standard topology optimization. This is because in the objective function, we minimize the compliance of the entire structure. But also interesting, you can see the robot always prepares for its next move. It adds material to support its next move, especially if you look at to the end. So for instance, here it placed some material here in order to support its last move. Without considering the intermediate structures, this beam will be unnecessary. Of course, with this computational scheme, you can play with different patterns of robot movement. On the left side, we could assume the robot could jump around, and then the layers will, the different color indicates different layers, corresponds to how the structure will grow over time. On the right side, we can assume there are two robots that move in parallel with the same speed. As you see, the structure, it creates more complex layout or more complex tool paths in order to support both robot platforms. So this is kind of a fun experiment. The next example I want to show is similar to the robot, but here we consider gravity of the structure itself. So we don't have robot mover on top. The objective function is again consists of two parts: the compliance of the final structure and the compliance of intermediate structures. Here, for the intermediate structures, the external load is the gravity, and the gravity changes over time because the structure is increasing. And we have this weighting factor R, alpha, to balance the importance of final structure and intermediate structure. So here I show results with different alpha values. So when alpha equals, if we go back, when alpha equals 0, it will be just the standard topology optimization to minimize compliance of the final structure. When alpha takes a bigger value, the importance of intermediate structures become larger and larger, and consequently the importance of the final structure may compromise. So if you look at the structure layout with respect to different alpha values, so from left to right side, we increase this alpha value. As you see, especially on this one, more materials will be accumulated to the left-hand side, because on the left-hand side, it is closer to the build plate, so it is more supported in order to minimize compliance during construction. So we can have a look at some values the compliance value. How does this compliance value change when a different alpha value is chosen? So these 4 rows corresponds to different alpha values, and we have 8 stages. So each structure is fabricated in 8 layers. So here, each of the value indicates the compliance at that stage. And the last column indicates the compliance of the entire structure. If we look at the compliance of the entire structure, when alpha value is 0.001, this value is very close to without intermediate structure, and even when alpha increases to 0.5, there's only a very small compromise in the compliance of the final structure. But with a compromise of only 2, the stiffness or the compliance of intermediate structures is increased dramatically. And this is in the design space, there's a big flexibility to accommodate compliance during construction without compromising the performance of the final structure in its intended situation. The next example is more relevant for wire and arc additive manufacturing. In wire and arc additive manufacturing, it is a direct energy deposition process. It involves very high temperature gradients. Normally, you could observe big distortion, or there will be prolonged residual stress. So here, the objective function is to minimize distortion. To simulate distortion, we use an inherent stream model, similar but simpler than what Professor Alberto has described previously. To measure distortion, this is our objective function. We minimize distortion of the top edge. So it is measured by the relative distance between 3 points. So the distance of each point to its average. This animation shows if we fabricate with typical planar layers on the left side or with optimized curved layers on the right-hand side, how big the difference can be when the displacement on the top edge is concerned. So I will let it run again. As you see, in this case, we have an overhang, and because of the residual inherent strain, it will distort. The more you add material, the more you go to the left side. And on the right-hand side, the optimized curve layer shows some symmetric behavior in order to compensate distortion. It tries to place material on the left side and on the right side at the same time. And if we look at the numerical values, on the left-hand side, the measured distortion is about 9.1, and on the right side, with this optimized layer, optimized curve layer, it is reduced by 2 orders of magnitude. Of course, you see there are some displacements to the top, to the reference. If there is no distortion, if there is no inherent strain at all, it will be this one. But with this inherent strain, there's a kind of shrinkage, but the flatness of this top layer, as in the objective function, is reduced to a very small. The last example I want to show is the same distortion minimization, but in 3D. So here, the example is left side is fixed. We want to find a structure in this box. The structure will be supposed to support load here, and we also want to have this surface as flat as possible. So to summarize, I present space-time topology optimization. It enables to concurrently design, structure, and do process planning. And the key here is we represent the fabrication sequence as an optimization of a time field. This is this time dimension is this encoding is analogous to topology optimization, which transforms structure design into a material distribution problem. So by space-time topology optimization using a density and time field, it allows to unfold the biggest solution space in order to maximize the performance of structures. It is a completely new research direction, so there are many questions remain to be answered. So here I identified 4 research questions. The first one is about theoretical ones, like the convergence of space-time solution, because we do discretization in spatial domain and in a temporal domain. How does this discretization influence the optimality of solution? This is unknown. The second, which is very important, is to develop accurate and efficient process simulation for specific manufacturing technology in order to minimize residual stress and thermal history, material properties related to thermal history. We also want to have process order that is manufacturing friendly. One of the topics we are currently working on is to reduce the weight variation. Of course, the last one is scalable computation. It is because we have an iterative process, and in iteration we have to do accurate process simulation, so it involves very high computation cost. We want to build a more scalable computational framework. Last but not least, I would like to give a shout out to my former postdoc, Wei-Ming Wang, who did this wonderful work. And I also want to thank my colleague, Fred van Koinen, for contributing his ideas. And this work, published last year, was awarded ISMO Springer Prize from the International Society for Structural and Multidisciplinary Optimization. With this, I would like to thank you for your attention, and I'm happy to answer any questions you may have.